Hi guys, this video is a continuation of our rotational dynamics notes that we've been doing. This is page 3. We're going to talk about angular momentum on this page. One thing to notice is we have a new variable. The variable L stands for angular momentum. Similar to the P with linear momentum, I don't know who chose L. I think they ran out of variables and they just decided to go with L. It is a capital L. One thing to notice is the equations here that kind of, they go together. So this momentum equation mirrors the angular momentum equation. P stands for momentum, L stands for angular momentum, M stands for mass, I stands for moment of inertia, V stands for velocity, and omega stands for angular velocity. So those two equations are similar to each other. This is for linear, this one is used for angular. Similar to with impulse, when we talked about momentum, we had this impulse. The definition of impulse is the change in momentum, how that momentum is changing. And we talked about one element of that is time. It's how much force are you applying, but also over what period of time. And so the equivalent to that, again, very similar, change in momentum, now it's change in angular momentum, is equal to torque times time. Of course, torque and force are related to each other, and time is time. So let's go ahead and jump into a couple of examples, just 2 examples on this page. The first question, a torque of magnitude of 0.1 Newton meter is applied to a solid cylinder of mass 5 kilogram and radius 0.2 meters, rotating with a 6 radian per second angular speed. Assuming the torque is applied in the correct direction, how long will it take the cylinder to come to rest? The first thing I want to do in this problem is I want to read through the question and write down what is given to me. So why don't you take a second, pause the video here, and write down what you know. Okay, so we know that we have a torque of 0.1 Newton meter. Mass 5 kilograms, radius 0.2 meters, the angular velocity is 6 radians per second, and then our equation for the inertial momentum is 1/2 mr squared. The reason it's 1/2 mr squared is it is a solid cylinder, and so when we have a solid cylinder, this is the equation we use. You don't have to memorize that. Okay, the question is asking how long will it take? So we are needing to solve for time. So if we take a look at our equations, we need to figure out which equation could we use to solve for time, given that we know all this stuff. So I'm going to use the change in angular momentum is equal to torque times time. It has time in it, that's why I chose that equation. Okay, well the definition for change in angular momentum is final minus initial. And so we have the moment of inertia times angular velocity final minus moment of inertia times angular velocity initial, and that is still equal to torque times time. Well, our final velocity, we want it to come to rest. So our final velocity is 0. It's out of there. Now we just need to use this part of it, the initial, and find it from there because since it's a 0, it's gone. And for our I, we're using 1/2 mr squared. Again, it's a solid cylinder, so 1/2 mr squared is the way to go. We're going to plug that in there and multiply that by the initial angular velocity and so forth. So now we're ready to take time to plug in those numbers and work it out. Do that. Plug the numbers in that you know and work it out and see what you get for time. Okay, so when you plug in the numbers, you have all this stuff plugged in from your information over here. We come up with the time is 6 seconds. And so what this is saying is if you are going to apply that much torque, it's going to take it 6 seconds to come to rest. Okay, next question is similar. The difference being that this question is asking for torque. How much torque do we need? We already know the time. And so similar thing, just working in a different way, looking at a different angle. Take a minute to read through the question and write down the variables that you know, and then we'll get to talking about how to use that in the equation. Okay, initial velocity is 0, and then you have all the rest of the information. It's accelerating from rest, that's why it is at 0. So once again, our angular momentum is moment of inertia times final velocity minus moment of inertia times initial velocity. And this time we're looking for torque. Also, this time we have a bicycle wheel. Since we have a bicycle wheel, it has a little bit of mass in the middle, but not a whole lot, right? Most of the mass is out here. And so we're going to use just the regular old mr squared for our moment of inertia. Because our initial is 0, we can get rid of this. And so now we just need to plug in mr squared for that. And we also need to talk about our angular velocity. Okay, so our capital I is mr squared. Angular velocity, remember over here, angular velocity is v over r. And so we're going to plug that in. And so when we do that, if you wanted to simplify it, you don't have to do this step, but if you wanted to simplify it, this radius and one of these radii will cancel. And so on the left-hand side, we're just left with mrv is equal to torque times time. We are solving for torque, so we could take it one more step if you wanted to and divide by t. And now you're ready to plug in your numbers. So do that. Plug your numbers in, work this out on your calculator, and see what you get. Okay, when you plug this into your calculator, you should come up with torque is 0.7. Our units for torque is Newton meters. I just want to take a second to talk about Newton meters and what those units are, because up here it doesn't look like we have Newton meters. Well, what do we have? Remember that force equals mass times acceleration, and that's measured in newtons, right? So I'm going to write this out. And so force equals mass times acceleration. Mass is kilograms, acceleration is meter per second squared, so a newton is a kilogram meter per second squared. That's what I have written here. If we look up here, we have a kilogram meter squared per second squared. That is a newton times another meter. So that's why we're getting this torque as Newton meters, it really is kilogram meters per second squared. Kilogram meters squared per second squared. But we say it in a little bit shorter way is a Newton meter. Next couple of days in class, we will continue to work on some activities involving things that roll.